All right, folks. Well, welcome back. I apologize for yesterday. There's one issue after another, so hopefully we can try to get caught up today. You'll be able to access Edpuzzle today. I contacted the folks yesterday, and they promised me then that they have were able to work out the server issues for on their end, and so you should be able to get into Classroom. I'm sorry, into Edpuzzle today, and um, and get that this assignment done. Okay. All right. So what we're going to do is we're going to try to finish up with this chapter this week, okay, and I'll talk about the exam that you'll take for this chapter towards the end of this week. We'll talk about how we'll do the review, and so that's something that they'll preview what we'll talk about towards the end of this week. But I do want to get started with chapter 12, so I'll post the chapter 12 material for you tomorrow, Thursday, or Thursday, in order for you to prepare for that. So please make sure you have take a look at that. Okay. All right. Come on by. I still have my office hours, 3:15 to 4:15 after school every day. So please make sure you come by and take advantage of that. I've seen only a couple of you so far, so please make sure you take advantage of that opportunity to get extra help if you need it. Okay. All right. Let's continue on then. Let's continue on then. We left off with this discussion of what we call the percent composition, and this is the percent composition. This is a way that we can measure, or a way that we can determine the amount of a particular element in a compound. So if you have a compound, remember compounds are made up of more than one type of element. We can actually figure out how much of that particular compound is made up of a particular element. So we can determine that if we know what the masses are. So for example, we take we take a sample of water or table salt, sodium chloride, and we break it down into their parts. So for example, let's take sodium chloride. Sodium chloride, that's the table salt, it's made up of sodium atoms, the element sodium, and the element chlorine. We can determine then how much sodium, how much chlorine makes up that particular compound by basically breaking down the compound and then measuring the masses. So we measure out a certain amount, we take a certain amount of sodium chloride, table salt, and we run a decomposition reaction. We break it down, we get certain amounts of sodium, we get a certain amount of chlorine. When we compare the ratio of those two and then we multiply it by 100, that is what we refer to as your percent composition. And so we refer to it, as I pointed out to you on the slide here, as the percent by mass, the percent composition by mass of an element, and we can calculate that fairly easily. If we know the mass of the element, and if we know the total mass of the compound, we can go ahead and find the percentage. The percentage, remember, is just part over whole times 100. Okay, so with that said, then the percentages are pretty straightforward. We worked through a problem like this on Thursday of last week. Okay, so here what we have then, if you keep this in mind, we are given a sample. Whatever the sample is, it's made up of magnesium and oxygen. Okay, so we did this here, and I just want to highlight this for you right now. So what we did here then is we saw then that whatever this compound is, it is magnesium and oxygen, and this is the total mass of that particular compound. Then what we did was we break down that compound. We ran a decomposition reaction. We broke it down. We measured the amount of oxygen that we get. So this is the amount of oxygen in this compound here, which we recognize it as magnesium oxide. Okay? All right. So this is the total mass of magnesium oxide. So we measure out a total mass of 13.60 grams. Okay. And then this is the total now. And then we get the mass of oxygen. We capture the amount of oxygen and we measure that out. We weigh that out. We get 4.50 grams. Okay. And so this is the mass of oxygen. You get the percentage of oxygen then. We just take the mass of the oxygen that makes up that compound over the total mass of that compound. And then we multiply it by 100. And whatever percentage we get here, that is our percent composition. Okay. All right. So with that said, then let's go ahead and let's take a look at a problem and let's work out a problem. And so we're going to practice this. Okay, so let's work out a problem here where you will be asked to find the percent composition. And so let's take a look at this particular problem here. Okay, so I'd like you to take a couple minutes, set up the problem, get an answer, and then let's compare our answers and compare work after you're done with it. So take about a couple of minutes, work out this problem here, and let's see what you get. Okay. Okay. Let's go ahead and let's see what you did here. Let's work this one out together. Okay. So let's identify what we're given here. So what we have here is we have some compound. This compound here is made up of aluminum and oxygen. And I think at this point, most of us will recognize that this is aluminum oxide. So I'll just write down the formula for aluminum oxide. All right, so we were told then that we take aluminum oxide and we combine it together. Okay, so our total mass then, so our total mass is 5.10 grams. That's our total. So make sure you keep this in mind that what we have here is the total mass, okay, of the compound. Okay. All right, so we break down this compound here. So let's go ahead and write down the decomposition reaction here. So we take this compound and we decompose it. That means we break it down, add some heat, break it down. We end up with aluminum and we end up with oxygen. And then you can go ahead and balance this reaction out yourself. Okay, I'll leave it up to you to do that. But we are told then that when we break it down, we are told then that aluminum, okay, the total mass of aluminum that we get is 2.70 grams. That's the total mass of aluminum in this particular compound. I think that we do the math here, and I don't think this should be too difficult for you. So let's go ahead and do this. Hopefully, you can find then the total mass of oxygen in this compound then by just subtracting the two. Okay, so let's go ahead and do that really quickly. 5.10 minus 2.70, and that'll give us 2.40 grams of oxygen. Okay, so those are the masses that we will need to work with. Okay, all right. So again, total mass of the compound. This is the mass, total mass of aluminum in that particular amount of aluminum oxide, and this is the amount of oxygen. Okay? So let's go ahead then, and let's calculate for the percent. So let's do the percent aluminum first. Okay, so the percentage of aluminum, okay, is going to be then the part that's made up of aluminum, the amount of aluminum, 2.70 grams of aluminum, over the total mass of the compound itself, 5.10 grams, and we multiply that by 100. Okay? And then we get our percentage in here as being 52.9% aluminum. So that is the percent composition of aluminum. Okay. All right, so we can do the same thing with the oxygen. So the percent oxygen in the compound then is going to be the amount of oxygen that we end up with, 2.40 grams over 5.10 grams times 100. And let's real quickly punch that into our calculator. Let's see if we get 2.440 divided by 5.10. And we end up there with 47.1%. So we end up with a percentage here of 47.1%. That is oxygen. Okay, so there it is. That's how we get our percentages. Part over whole times 100. Okay. Now, probably many of you will recognize then that once we calculate for the percentage of aluminum here, we really don't have to do the second calculation as long as we are aware then that we only have two. If there are only two elements, that means then whatever this percentage is, which we calculated here by taking the part of oxygen and dividing by the whole, we can get this percentage by taking this percentage of aluminum and subtracting it from 100%. So we take 100% minus 52.9%, and we will end up with 47.1% as well. And so you can go ahead and do that ways if you want to, and I think this would be probably the preferable way to do it. It's a little bit more straightforward, a little bit easier, as long as there are only two elements in that compound, meaning as long as we have a binary compound, you can go ahead and do it that way. Okay, but please make sure then that you show the work in order to get this done. Okay. All right. So with that said, then let me ask you to consider this. Okay, and I'm going to erase this. Hopefully, make sure you write this down, folks. If not, make sure you pause it and write it down. Okay, in your answer. Okay. Let's consider this here. Okay, so we know then that the element here is aluminum oxide. I give you the formula here. Okay. Okay. The question then is, what if we don't have this mass? If we don't have this mass, we can't solve for that one. We can't get that one. Can we still obtain the percent composition if we know this much about the compound? That is, if we know the formula of the compound. The answer there actually ends up being yes, and for one very important reason. So let's continue on then. One very important reason, that is, remember, when we learned about these ratios here, we learned that they represent the fixed amounts of aluminum and oxygen in that particular compound. It's the fixed whole number ratio. We learned that when we talked about Dalton's law, Dalton's theory, that these subscripts here represent the fixed whole number ratio that represents the ratio of aluminum to oxygen for this particular compound. Okay, so that's what these subscripts tell us. Okay. All right. So with that said, then, if we take a look at, change that over. Okay. We can actually obtain the percent composition without having actual masses. We don't have to run any chemical reactions. We don't have to do any decomposition reactions in order to obtain the percent composition if we know the formula. The reason for this is that if you consider this, Kim, and I want you to consider this really quickly. The percentages of an element in a compound, the percentages of the elements in a compound will not change depending on mass. So for example, if you take water here, water we know then is in a ratio of 2 to 1, okay? And the percentage by mass then is given to you on the slide here, 11% hydrogen, around 89% oxygen. Okay? That percentage doesn't change whether you have a drop of water, as we have here, or you have a whole ocean of water, which is what we have here. The percentages will still be the same. Now, obviously, the total mass of this amount of water, the whole ocean of water, is much, much greater than the mass of a single drop of water. But understand this, the ratio here, the percentage of hydrogen to oxygen will always be the same, regardless of whether you have a little bit or a whole lot of that compound. That means then this formula here, if we are able to recognize that, then okay, we can go ahead then and use this formula here, okay, to obtain those percentages. So as long as we know what the formula is, we should be able to obtain those percentages in a given compound. Okay. All right. Let's go ahead and practice that then. Okay, let's go ahead and let's take a look at how that works. Okay. Okay. So how we're going to do this here then is we're going to, instead of using actual masses, if we know the formula of the compound, which represents, we can calculate for the molar mass. And we know what molar mass is. We talked about molar mass early on in this chapter. The molar mass of a compound is the total mass of all the elements in the compound. And we can obtain the molar mass of an element by just looking at the periodic table. And so there it is. We can find the molar mass of a particular element in the compound itself, which means then we can still obtain the parts of the whole. And so we can still calculate for the percent by composition here by using the mass of 1 mole of an element in that compound, okay, which is the molar mass over the molar mass of the total compound. So let's go ahead and write this out here. So the percent then, let me write this, the percent composition then will be the molar mass, and just simplify it here, molar mass of an element, of the element, over the molar mass of the compound in which that element is a part of, okay? And so times 100. So it still ends up being part over whole. But this time though, we're using molar masses instead of actual masses, and we can obtain percent composition in the same way, okay? All right, so let's go ahead and let's take a look at an example here. Take a look at an example here of a problem where you would have to do that, okay? All right, so we have here propane. Okay, propane, I give you the formula for propane, okay? And the formula for propane has 3 carbons and 8 hydrogens in it, okay? The first thing we need to do then is we need to figure out then what is the molar mass of propane, which is 3 carbons and 8 hydrogens. So if you add those all together, okay, you should end up with 44 grams per mole. If you cannot get that number then, please make sure then you come by and you see me and get extra help with that, okay? All right, and so with that said then, let's find so this is the total mass. Again, this time though, this is the total molar mass that we're dealing with. And so therefore, we need to also find the total mass of 3 carbons. Okay, so the total mass of 3 carbons is going to be 36 grams per mole. And then same thing with hydrogen. We have 8 hydrogens. Okay, total molar mass, there will be 8 grams per mole. one hydrogen has a molar mass of 1 gram per mole. We have 8 of them in this particular compound. And so therefore the total molar mass from hydrogen is going to be 8. Same thing holds true here for carbon. Carbon, the molar mass for the element carbon is 12. We have 3 carbons in this compound. So the total molar mass contributed by all 3 is going to be 36 grams per mole. Okay. All right, so those are our total masses there that we're going to use. Those are our masses we're going to use. So let's go ahead then, let's calculate for the percent of carbon in this compound here, which is going to be then the mass, the molar mass of carbon, which is going to be 36 grams per mole. That's the total molar mass due to carbon over the total molar mass of the element compound itself, which is 44 grams per mole. And we're going to multiply that by 100. Okay, and then when we plug that in, our answer here then is going to be 81%. That's going to be the percent composition of carbon. Okay, so doing the same thing for hydrogen then, folks. The percent of hydrogen then is going to be the total molar mass of hydrogen in the compound, which is going to be 8 grams per mole, which is what we have here, over the total mass of the compound itself, which is 44 grams per mole, times 100, and we get here then a percent composition of 19%. Okay. All right, so that's how we obtain then the molar masses of compounds, of elements in a particular compound, if we know the formula and if we're not given actual masses. And so the same thing holds true here. If you notice, this is a binary compound, so instead of doing the second calculation here, what we can do then is we can take the percentage of carbon, of percent carbon, and subtract that from 100, and we will still get 19%. All right, so on the exam, folks, make sure then if you choose to do it this second way here, that you show me the work that you get here, okay? All right. Okay, let's go ahead then, and I would like you to try a problem here, and your homework for tonight is going to give you a chance to practice this some more. So let's go ahead then, and let's try a problem here. I'd like you to do number 28 in your problem set. Okay, take about 3-4 minutes to work this out here. I give you the formulas for each one of those, and so make sure you work that out, and let's see what you come up with. Okay, so go ahead, work out the percentages, the percent compositions for each one of these compounds here. Okay. All right, let's go ahead then. Let's take a look at the first one. Okay, so let's do the first one and let's work that one out. Okay, so we have then the formula as being iron 3 oxide. Okay, so first of all, let's find the molar mass of iron 3 oxide. Iron 3 oxide, if you add up 2 irons and 3 oxygens together from my periodic table, I get 159.6 grams per mole. That's the molar mass of this compound. Okay? All right, for the molar mass of iron then, so we have 2 iron atoms in a particle of iron 3 oxide. So we will get the total mass of that, which is going to be 111.6 grams per mole. And then we do the same thing with oxygen, the 3 oxygen. Then we have then, let me go and calculate that for you, 16 times 3. Sorry, real quick. 16 times 3. We get then 48 grams, 48.0 grams per mole. Okay. All right. So calculating then for the percent iron. Let's do that first. Okay. And so iron then is going to be, it's a part that compound is made up of iron, which is 111.6 grams per mole, over the total molar mass of the compound, which is 159.6 grams per mole, times 100. And so we get a percentage there then as being 69.9%. Okay, so that's the percent composition of iron. Doing the same thing for oxygen then, we have then 48.0 grams per mole. That's the mass, total molar mass of oxygen, over the total mass of the compound, which is 159.6 grams per mole, times 100. And if you plug that in, you'll get your answer then as being 30.1%. Okay. as the molar mass, and I'll check that really quickly. Divide that by 159.6. Sorry, let me go backtrack here. 0.6. Yep, so we get 30.1%. Okay, and again, this is percent oxygen. Sorry, to get the percent oxygen, you can just go ahead and take 69.9 and subtract that from 100. But I wanted to show you both ways here in order to see how allow you to see how that works. You can do it both this way here to get the percentage of oxygen, or you can just take this amount here and subtract it from 100, since this is a binary compound. Okay. All right, let's go ahead and let's take a look at the second one. Okay. So we have mercury oxide. Okay. So the total mass there of mercury oxide is going to be 216.6 grams per mole. That's the total molar mass. The mass of one mercury, since in mercury 1 oxide, mercury 2 oxide, we only have one mercury. That's going to be 200.6 grams per mole. Okay? And the total molar mass of 1 oxygen is going to be 16.0 grams per mole. Okay. All right. So let's go ahead then. Let's calculate for the percent of mercury in mercury 2 oxide. That's going to be then the amount of mercury, 200.6 grams per mole, the molar mass of that particular mercury atom, over the total molar mass of the compound itself. Again, part over whole times 100. And we get a percentage here of being 92.6%. Okay, so that's what we have. That's the percentage of mercury in this compound right here. And then doing the same thing for oxygen then, okay, that's going to be 16.0 grams per mole over 216.6 grams per mole times 100. And we get a percentage here of being 7.4%. Okay. Yep. And again, if you wanted to get the percent oxygen, if you didn't want to do this second calculation here, you can just go ahead and take the 92.6 here, subtract it from 100, and you're going to get this percentage as well. Okay. And so that's how we obtain the percent compositions from the formula. Okay. So with that said, then please make sure you include this in on your paper, and I'm going to assign you one last problem to do in just a moment, and then you'll submit that for today. But practice the homework for tonight. The homework for tonight is going to give you a chance to practice the percent composition here, and then come by after school today if you can to get extra help with this. Okay. All right. So very good, folks. Hopefully you'll be able to. Things will work out. I don't anticipate any more technical issues today, at least, and so everything's been running pretty smoothly so far. And so watch the video, get the homework done, and come by and see me and get that extra help. Okay. If not, I will see you folks tomorrow.